Alrighty, let's get going. I want to do another session. I have a small updates. Over the past few days, I've been running this learning bot that I started on the last stream, and I made a slight change, or a couple slight changes, and that led to different curves on this screen right now. So let me show you one at a time. So what this is plotting is this is the reward that the bot receives at the end of the game. So plus 100, 1e plus 3, plus 1,000 is a reward for winning a game. 0 is a reward for drawing the game, and minus 1,000, which is not shown on the screen, is for losing. And this is playing against a really bad bot, and I'll get into that. The main problem is that it was playing against such a bad bot that it's sort of succeeding at the learning task, but then if you play the bot online, and I've noticed a lot of Lichess accounts have been challenging my bot online. It's really like my bot is really bad with this evaluation function, and I think it's like my thinking now is that even though or because it's doing well on this learning task, and maybe there's room for it to do better, but it should be doing pretty well. I think it's just because the opponent is so bad, like the opponent it's training against is so bad that it's uh, even though it's good at playing against that, it's not. It's like embarrassingly bad against a human or anybody who thinks for more than like a second about any given move. But let me go over what the different variants are that are. Maybe variant is a bad word right now, but all the different types of the learning algorithms I came up with. So the first thing I did at the end of last stream is this. This is the. Oops. Why is it showing two things? Oh, sorry. Yeah, so before the last stream, we had this linear model. So this was just using the features that I gave it. And this is the results, and it reaches a score of like an average of around 600, which means it's getting 600 reward per game. So it's winning quite often, but not all the time. And then if you add threshold features, you get a little bit better. You get up to like 700, almost. No, it says 664 here. So threshold features is what I did on the last stream. That's where I took some. By features I meant random features. So this is where I took random functions of the original raw game information and threshold it. And that creates a nonlinearity, but it creates kind of a weak nonlinearity. It's not ideal. None of this is ideal because really what you should be doing is learning the nonlinearities, which is like a full neural network. But for now, we're sticking to simple random projections. Then I added Fourier features. So the difference here is instead of using just thresholding a random combination of the original features, I take a cosine of them and then add a random offset to them. This comes from a famous paper that won the NeurIPS Test of Time Award back in 2017. So I guess that means it came out in 2007. And in that paper, they showed that this works almost as well as neural networks, if not better. Sometimes it works better than a full neural network, and it's a lot lower cost. It's not as expensive for the computer. And the idea behind using a cosine transform is so the threshold idea that's the blue curve is it loses a lot of information, right? So if anything is either below or above the threshold, then it becomes either 0 or 1, and it doesn't differentiate between anything that aside from those two bits of information. Whereas a cosine allows you to essentially, you can think of it as like approximating the Fourier transform of a function, or if you ever look at like a spectrogram, which is where you break apart like a sound into all the different frequencies. That's essentially what we're approximating. We're approximating a random sample of the frequencies of the signal. And the signal we're trying to recover is like this score of like whether a position in chess is good or bad. So anyway, once we add Fourier features, we get this red curve, and it looks better. It ultimately ends up with the score, not much better. So the score is like 700 something. You can see it here. Oops, I can't. While I hover over it, there's a column in this preview that says smoothed. That's like the smooth average score at this time. And you can see that it reaches around 700, which is the highest we've seen. And then I tried a couple other things that didn't make as much of a difference. So I tried adding a high temperature, which is actually technically should be called a low temperature. So I made a mistake there. But I make it so that rather than randomly choosing a feature, you choose randomly choosing a move based on the score, which is the way the bot is currently set up. I set it so that it chooses the best move, or randomly chooses among the best moves. And that made it worse, but I don't know if it's going to be better or not. So, and then this other run was a different initialization. So you can ignore the high temperature stuff. I'm going to remove it. I think I'm going to keep it as is with the low temperature. Well, I'm not sure. But here's my point. Okay, so my plan for today is that I want the ultimate goal is to, I don't know if I'll be able to pull this off in, I have like roughly an hour before I need to go do something else. I hope to allow the bot to play itself, right? So right now it's playing a really simple bot. And in fact, I'll just remind you what it is. The bot that it's playing against is in the code. It uses scores, where is it? It's around here. Yeah, these are the scores. So it just uses the standard material values for the pieces. So this is pawn, knight, bishop, rook, queen. This is king. I got to get rid of that, but for coding reasons, it was easier to keep the king there. And then this is just a checkmate. And everything else is 0. So this is like the worst possible. Well, it's not the worst possible. It's one of the worst possible evaluation functions. Sorry, I shouldn't say that. It's actually a pretty good evaluation function. It's a really bad score to make a decision based on, because you will do things like taking what appears to be a free piece when the piece that you capture with can be recaptured, and then you end up doing something like trading a queen for a pawn. And we've seen this before, right? Before we had look ahead, we also had the same problem. So this is the black playing the black pieces, and playing the white pieces is our bot, which is initialized to the same thing but is able to learn other ideas. And let me think. So right. So the problem is that as our engine gets good at playing against this terrible bot, it's good that it can beat this bot, but it can employ strategies that are not good against humans, like setting up one of these queen pawn trades, and then this engine is forced to take that trade. In fact, I think this came up before in another stream, but this is similar to like the rules of checkers, where in checkers, if there's a capture available, you're forced to take it by rule. By rule, you have to make captures in checkers. So in chess, you're not allowed. You're not forced to do that. That's silly. But that's kind of the game that's been set up. So engine white here is learning weights that do well against another bot playing checkers. In fact, this is like, what is that analogy? Or it's like we're playing chess while they're playing checkers. Like that's basically what's happening. So the solution to this is to have stronger opponents for our bot to train against. And then we can really see how strong our simple neural network can get. And again, it's simple because it's using these random features and is not able to learn more complex things on its own. It just has to hope that the features that it gets are useful enough. So anyway, so now we're going to, hi Envy. Hi, we're going to, all right. So we wanted to play stronger and stronger engines, and the strategy that people like Google have used or to train like AlphaZero is to have it play itself, right? So what I want to do, and in fact, I think I already implemented it. Yeah, so I implemented a version of this. So we're going to check, this is the main loop of the training algorithm. So in this loop, we play game and we do some training. And what I'm going to do is I'm going to check some condition. I don't like the condition I wrote. I wrote this last night just to try to write something down. Every few iterations, or whatever this condition is, it's going to update black to match the white weights. So I have engine black weights equals engine white weights. So we set the weights, we essentially set the opponent to be a mirror of ourselves. And then And then what should happen when we set it this way is we're going to now be evenly matched against our opponent. So on the surface, I'm going to comment this out for now because I don't want to do this yet. So the reason I don't want to do this yet is because it takes too long to train this. This takes hours. And I'm hoping to get it down to be faster to at least get it so that, like, I would be okay, like, making a transition to, like, let's look at the Fourier Features one just by itself. Like, I would be okay if it reaches, like, a score of 500. How long did this take? I think it took 5 hours. Oh, I ran this for 40 hours. Okay, that took forever. It's like an hour in. I mean, so it starts out, you should start out around 0. Hello, Doug Guy. Welcome. So I think if the score's around a few hundred, then it's like winning more often than it's losing, and it's not winning more often than it draws. Right? They'd have to be above 500 to get that. But at that point, I think I'd be comfortable sort of increasing the strength of the opponent. But what you don't want to do is increase the strength of the opponent right away, so that learning becomes too hard. Right? If you increase the strength of the opponent right early on, then there's going to be no signal for us to figure out how to improve our bot, or not us, for the learning algorithm to learn how to improve the bot. So we really want to gradually increase the strength of the opponent. But anyway, so we want to gradually increase the strength of the opponent, but we're learning it's very weak right now. So you just joined. If you just joined, then right now it's the current opponent. So the bot learns to play well against the current opponent, but the current opponent just takes whatever pieces are available, even if a piece can be recaptured. So it'll trade anything for anything, and that's not good, right? It's just trying to increase the material count for the next turn, not considering what will happen afterwards. So that's the initial bot. These are the weights for material imbalance. This is the weight for checkmate, and then all the other information is treated as nothing. It has 0 weight, is not considered at all. So it's quite weak. It's quite weak to begin with, and what we're seeing is that, like, all these different models are learning to play against that really terrible bot, but we need to set up the game so that it can get better training. Yeah, the question is the intended end result is that it learns to protect pieces? Yeah, I think I would be happy at that level. I mean, we're not looking for AlphaZero quality play. We're looking just to, like, play like a human, because there's nothing in the information that is given that directly says how to protect pieces, like what it means for a piece to be under attack. It doesn't even know anything about, like, what a diagonal is or what a file rank is. It doesn't know that rooks. I mean, it sort of knows how rooks move because it knows what the next legal positions are, but it doesn't know that, you know. Yeah, it doesn't know how pieces can be captured, or rather, I shouldn't say that. We're not giving that to it, so it should learn by playing, and it's not learning that right now. It's just taking whatever pieces are available, and not considering that the piece that it just took with is now under attack. So I would like to see, like, there's other AI methods that I've done in previous streams where you explicitly program it to look ahead, and here I'm trying to just use machine learning to try to have it learn to look slightly ahead. And, you know, the real strongest bots out there do both, right? So you can both explicitly program how to look ahead, and you can have it learn to evaluate a position. But to evaluate a position well, you have to have some notion of looking ahead. Maybe not precisely looking ahead, but just like a notion of whether a piece is safe. So yeah, that's the plan. So here's the solution, right? Like, my problem is that this is too slow. I don't want to have to wait hours and then until it learns and then replace it with a better opponent. I want to wait. I don't know how much faster we can make it, but I want to implement this method called experience replay, which has been it has had a renaissance in recent years. It was invented a long time ago for reinforcement learning, but and it's not a very complicated idea. So in reinforcement learning, the traditional approach is that as soon as something happens, you learn, you update your model based on what you observe. But experience replay, what you do is you store, like, a memory of a bunch of stuff that's happened, and then you update when you learn from all the memories, not just from the thing that just happened. And that's all I want to implement. So what people have found in experiments and with some theoretical analysis is that that helps the learning work faster. So we're going to try to implement that. So my plan is to implement that and then see if this curve grows any faster when I run it. Actually, I guess the comparison would be, maybe I'll turn off the high temperature. So I'll set the temperature to 1, and that'll be right like the red curve. Let's see. Temperature equals 10. All right. So, so my plan is then to implement the replay, and I'm going to do it in the learn function. Does it have any opening knowledge? No, I'm not encoding any. Yeah, again, the strongest engines use all the tricks. So they have. Well, I shouldn't say that. You can build a very, very strong engine by using all the tricks. So one of the tricks is using opening knowledge, and there's so much theory that we know that's been studied for centuries. Although we are learning more from engines, but the yeah, I mean, I think having an opening book makes an engine just a lot stronger with kind of for free, right? Because like an opening book's not that big, you can just download it. It's available on Lichess now. And it's pretty easy to program a computer to follow the book, right? That's really straightforward. So it's like I want to leave that out, not because I don't think it's it is helpful. I just think it's not too exciting to me as a computer scientist. There's probably some clever things you can do that make it exciting, but on the surface it's just like a lookup, so that's not too exciting. Yeah, I agree. I mean, openings are really challenging for the old traditional AIs that don't, that just look ahead, right? Because if you just look ahead 3 moves in an opening, every move is legit, right? Every move, is 0.000 basically. Right. Even moves where you you give up material, like a lot of them are like valid gambits, so it's really challenging. As a player, it's been quite fascinating to see the evolution over the last decade. Yeah, that's been exciting to see. Okay, so let's see. So here's the learn function. So in this function, we receive information and then we do learning. So rather than, so let me just mark some of this stuff. So this is, what is this? This is max future score. What am I doing here? Max future score equals 0, max. Oh, okay, so this appears to be, do QLearning step. Wait, I guess we want to compute QLearning look ahead score. And then here we want to update the actual weights. All right, so I'm going to add a bit here. So rather than just directly running the update, we're going to store position in buffer, and we're going to create a buffer. Let's see. So here's where I need to do a quick search to see if Python has Python collections circular buffer. So the idea behind the replay buffer is you want to store something like the last 1,000,000 positions you've seen. And we can pick a smaller number if that starts blowing up my hard drive, my laptop. But see, I don't want to have to install a separate package, because it's actually a really simple data structure. Oh wait, so what I'm saying is that if you want to store the last 1,000,000 positions, then the idea is that when you have less than 1,000,000, fewer than 1,000,000 positions in your buffer, you just add it to a list essentially. But once you have 1,000,000, what you have to do is find the last one that the earliest one that you added and delete that and replace it with a new one. And that's that requires keeping track of stuff. So I guess what I'll do is I'll implement a quick circular buffer. I'll just put it here, I guess, since there is Okay, since is that even what it's called? Okay, I don't know. It's fine. I guess it should be a list. Yeah, I want it to be. I wanted to extend the list. All right, so I'm just gonna do self.super. Actually, don't remember the syntax here. Can we do this? Is it like this? That can't be right. Okay, let me just look at how to do this. Python subclass. I always forget what the right syntax is. All right, so they're saying, okay, that's the base object, and then this is okay. Super init. Okay, so super is the thing you call by itself. Okay, that's all I need to do. Super like that. All right, so I'm not initializing with. Oh no, I need to. Let's call it. So that's the first entry, and I guess what I'll do is def. All I want to do is add to this, so I'm just going to create an add function. Should I use that underscore add? I'm just going to create something that's safe to be, that won't be used previously. Okay. So I'm going to say if I hope this works. If the current length of the list is less than, oh, I know, I need a max size. Then we're just going to add it in the normal way. So it's going to be self.append x and cursor would be the length. I guess I should swap these lines. Okay, so I think that should work. And then okay, right. So if the buffer is full, so let's just do some. I'm gonna add this for now to debug it, just to make sure we get this right. And we're saying, okay, now the cursor will be on the last entry. I think actually cursor I can leave as 0. So cursor is going to be always at 0 because that's the first thing that was added to the list. And then we're going to say self cursor, oops, x and self cursor plus equals 1. Oh no, let's do it this way. All right, so this should work if I didn't do it wrong. I don't want to spend too much time on it because it's like this is like would you learn this like sophomore year? It's like CS2 stuff, which is why I'm a little rusty on it. But I do want to do a test of it, so let me write a test function. Just put it in my test engine class. It's not a class, my test engine file. So test circ buff. Do I need a self? Yeah. Okay. And let's create a list of stuff. Let's say, let's import, oh, maybe I should put import up here. Okay. Buffer equals circle buffer, and let's set the max size to, let's set it to 4, and we're going to say buffer.add item oh shoot. All right, so after adding ABCD to the buffer, we should get ABCD in the buffer. And then what we should see, if I continue adding let's do that. So then, okay, what we should see, this is not a proper test because I don't want to, well, should I just do, I could write a proper test, so I'll just do assert, self.assert equal tuple buffer, and it should be A, B, C, D. So we want the buffer to be A, B, C, D at that point, and then at this point, so the idea of a circle buffer is that if we keep adding stuff, we should get E, F, replacing the oldest one and the second oldest one. Let's try this. Will it work? If it works, then we can continue. Why is it so slow? All right, it passed. Why did it? What? Oh, it didn't run the right test. Oh shoot, I put this inside of a different thing. Okay, I had to change the indent level and try again. Yeah, like I had indented it too far, so it thought it was part of the previous function. Or I shouldn't say it thought it. I wrote it as part of the previous function. That's why it was too slow too, because it shouldn't have been so slow. This is a simple test. All right, and it failed, which is more, it's failed because, and that's more likely to happen when you write a new thing. All right, so it doesn't even have an attribute max size. What am I doing wrong? Max size. Circle buffer max size. Even this tooltip says there's a max size. Oh. Right. I don't know. I forgot to write that. All right. Still, why is it so slow? Okay, it passed. So, all right, it said buffer is full, which is what we want, and I'm going to get rid of that now. But yeah, A, B, C, D, and then E, F, C, D. So yeah, replace the oldest ones. Which is what we want. So like, this is what we want. We want to set like the buffer size to be 1,000,000, and when we see 1,000,000 positions, we're going to save all of them. But then when we see the next one after that, we're going to replace the very first one we saw. And so we'll always keep the last 1,000,000 positions that we've seen. And I think this should work, so why don't we start using it? So in QLearning, what I want to do is store it in the buffer. So do I have a buffer yet? I don't think I created one yet. Features, this is the initialization. So here I'm going to say self.buffer equals circle buffer, and let's say buffer size, and we'll give a buffer size parameter. That buffer size equals, let's set it to, see in the paper that, was it DeepMind? I think DeepMind published a paper that used this to learn Atari games. They used 1,000,000, but I'm not DeepMind. I'm running on my laptop. I'm gonna just do 100,000. 100,000 positions. Our games are like 50 moves or so. What is that? So we would store like the last 2,000 games. That seems okay. That seems okay. We can change that later if we feel like it would help. All right, so now where am I? The buffer. Okay, so here's the learning function. So self.buffer.add item, and we're gonna add something that's a little funny, which is all the information we need here. So we have the reward, the previous board, the previous move, the new board, the learning. So what do we actually need here? I think we need this, the features. We need this also. How do we make this efficient? Because one of the challenges is that like this stuff, finding the legal moves, trying all the different moves, that's slightly expensive, especially if we want to do this for lots of positions. Storing a chessboard object is kind of expensive. Like if I could just store features, it would be nicer, but we need to know these. I don't know if we can get away with it. I think we have to keep it, so we're gonna keep it then, and I'm just gonna have to hope that the boards are not, like when I pass it the board, do I pass it a copy? I don't want it to be something that, so like, you know, Python, like many languages, keeps objects in memory, and if you pass that object to like a list, if you store it in a list and someone changes that object, it changes the copy in the list as well. So I want to make sure I keep a copy of it, but I don't want to copy too much. Yeah, here I'm making a copy, but then when I do learn, I just pass in that position, and I use it more than once, so I think I have to make another copy. It's okay. It might take up some memory, but for now this should work. So we're gonna say we're gonna try to add all the information in a tuple. Can I do this? So I'll do reward prevboard.copy new board. Oh, maybe I didn't need to make all these new lines because it's just 3 things. Is this correct? So I just need the reward that we actually received, the previous board, and the board that resulted after the move. Traditionally in reinforcement learning, you also keep the action that you made to reach the new position, but I don't actually care because in chess, because it's deterministic, you know, well, it's not really deterministic because, interesting. Do I need to know the action? Let me think about this for a second. So when we make an action, we consider what happens after we make the move. So the question is, I wonder if there's a bug in my current implementation. So this is the formula that QLearning uses. So this is the score of the action that was taken this is the reward that you received for that action, and this is like this is an estimate of what future reward might be possible, and this is what your previous estimate was. Actually, I don't know why I wrote this. Oh, I was in the middle of writing. I'm just gonna cut that out. Okay. But now, like, this is my update, but this is the score. Sorry, this is the score that we received. This is the maximum future score. I mean, it is learning. Let me try to find my slides again. Let's see if I had anything different. Because yeah, I'm thinking about this. This is a little, yeah, I gotta get this right, because this, it doesn't particularly affect the experience replay implementation. It's more about whether, I mean, if there's a bug in what I did, then there would be hopefully better performance regardless of whether I add experience replay, which I still want to do. All right, so these are the slides. I had, this was the function I was implementing. So here, I have the reward, the maximum score for the next position, and then this is the score, the estimated score for the current position with the action that was taken. And I think this is where and the features for the action that was taken. Is that what I'm storing when I store? I don't know. Let me think. So I guess it matters more what I do here. So here I'm saying white positions, white moves. Oh, so I have the moves. Oh, okay. I'm passing it the moves. Am I using those moves? Oops. Come on. Oh, why is it doing that? That's so annoying. All right, I have to jump back here manually. Previous board, previous move. Okay, so where am I using previous? Oh, right. Okay, so here's the features for the previous move. Yeah, okay, I am using it correctly. Yeah, okay, I forgot. All right, so then action score, previous board, previous move. Okay, that's correct. So then I guess I can just implement this as I was doing. Okay, I apologize for the getting confused, but I think it's correct. I think because I implemented this this is the action score for the previous board and previous move, so it is receiving the move as needed. And the max future score is also looking at the new board and the move. Okay, I think this is correct. So this actually is fine. So now, here's the thing about experience replay. So rather than doing QLearning on the move, on the position we just saw, what you do in experience replay is you randomly sample a set of moves or a set of positions you saw in your memory. So it's unlikely to be the one you just saw, but you know, it's like more likely to be representative of the different moves you'll see throughout your run as an agent or as an AI. So to do that, I'm going to have to pull out, I guess what I'll do is, I don't know, I can do this a really slow way by just like looping over and like putting this whole thing into a loop. I don't know if I have a choice but to do it the slow way. So this is where it might be useful for me to, instead of storing this stuff, I could store some vector representation. I mean, this thing I can store because that shouldn't change. Oh, yeah, it will. Yeah, we have to compute the action score using whatever the new weights are. So it's actually, that will change. So yeah, I don't know if I can actually, okay, I'll just implement the slow way. It won't be much slower than how it was now. Hold on one sec. Fix my light. Okay. Okay, so I'll just implement the slow way. So we'll have a batch size. I'm just going to do 4. And so we store the position in the buffer, and then we hope this works. So I now need to find don't like the variable naming here because there could be bugs introduced. So I'm going to call this batch board, and this I think is okay. New board should be batch board. Move is what is move? I'm missing prev move. I need prev move here. But yeah, so now batch. Okay, so let me see. So I'm going to say reward. You know what? I'm introducing more bugs with this, so I'm just going to put this back to new board. What's the best way to make this safe? No, I'm not going to introduce no new bugs. I'll fix it. I'll do it correct. So this is batch board. This is, so what is for move in moves? That I leave as is. Prev move, we're going to call it batch move, and prev board, we're going to call it. Uh-oh. What was this before? This was new board. Yeah. Okay, batch new board, batch move. This is let's just give it the full name. Batch prev move, batch prev board. Oh shoot. Okay, this batch prev board. I might have messed so much up now. I mean, it's actually good that these are underlined because it means that, but it still could be messed up. All right, so then we update the weights. We're not going to do anything smart with combining. Well, okay, I can think of this as a gradient, so I can add them all up, but I'm just going to take gradient steps. So reward max feature score. Okay, this action score should be batch prev move and batch prev move board and batch previous move times descriptor. And now I have to define these things. So I'm going to grab them out of this buffer. So batch, reward I'm keeping. Oh, that's bad. All right, reward, batch reward. Okay, batch reward, batch prev board, batch prev move, batch new board equals. All right, we're gonna do self.buffer. Do I have that random state I had saved last time? Let's just use it. Oh, no, I don't have it. It's not stored. All right, let's just. I want to keep this. Let's call this self.random state, and now this needs to be self. I'm a little nervous because I'm changing so many things right now, but I think it should be okay. And now I'm here, right? I want to so I want to do self.random state dot choice, and it's just going to be self.buffer, and we're just going to choose one thing, and I don't know for sure what choice does. So it's just choice. You get A, size can be none, replace can be true, by default true, P is none. So A is the array, which is fine. Size is output shape. If default is none, if single value is returned, that seems fine. Replace is true. The probabilities, oh, that's cool. Well, anyway, I want a uniform sample. So this should do, well, I've now built what I intended to. Now let's see if it does. Now, how do we know if it's working versus not working? Let me set up the actual learning task to do what I want. So I set it to be temperature 1. I'm initializing it to these weights. I guess I could just start running it and see what happens. Now let's see if it actually runs, because this, wait, well, let me think. What did I do? So experience replay is on. I currently don't have it replacing the black engine with the new weight, so it should just be playing the terrible starting engine. And let's see if we so what I expect to see is a curve similar to this. Actually, you know what I can do? I can turn off, if I set the, okay, here's the test. Wait, how many hours did this take? If I set this to, sorry, this is relative. Let's do wall clock. So at like 12, oh wow, okay, so this was from 12 to 6 p.m. So this was like at 4 p.m. That was around last time I streamed. Oh shoot, this interface is not perfect at all. Okay, so around 4 p.m. I started running it. Around 5 p.m. it was like that. Well, that's the level we should, I mean, that's what we want to compare against. But I don't want to wait a whole hour. But all right, I don't know. Maybe I don't have any choice here but to just run it. I was gonna say I could turn off all the experience replay stuff by setting the maximum buffer size to 1, and then it would behave oh, batch size. Did I not just set that? This doesn't exist, right? Yeah. I was gonna say that the batch size needs to be 1 also, but batch size equals, let's do 10. All right, those are just some magic numbers I threw in, and I'm gonna hit run. Let's just see what happens. It'll probably crash as usual. That's like what happens when you run code that you wrote for the first time. Oh shoot, I mean, I didn't run the right. Okay, well, it passed the old test I ran, but now let's run a circle engine. Okay, and it says it must be one-dimensional. All right, let's look at that line of code and see. I suspect what's happening is because it's a list of tuples. Why can't I debug this? Something's funny about my interface. I might have changed something for streaming that made me lose something. Well, the debugger also activates as soon as there's a crash, so that's, since I want to stop on the line that it crashes, it's actually not that bad. Okay, so I want to look at this thing. No, wait, it's this, right? So that's the line that's not working. So let's do self.buffer. It is a list length 1. Okay, so why is it complaining? Yeah, so it must be one-dimensional. The buffer is one-dimensional. Let me just put in a list of, let's just try this. So if I do A, B, C, so it's happy to choose from that, right? Randomly, it's sometimes it's A, sometimes it's B. But now what if instead I make one of them a tuple? So let's call it A, B, C. So now it's a tuple. That's so annoying. Okay, so we have a tuple, and why don't we just copy this? So now I should be able to choose one of these. I'm going to name them differently so that we can tell they're different. F, G, H, I. Oops. Oh. Okay. Evaluate maybe. Yeah, it's not happy because it thinks it's a. Okay, I think what's happening is it thinks it's a two-dimensional array. So one way to do this is to just take a random sample, a random integer. So I'll just say self.random state .rand int, and we'll do high equals length of self.buffer, run. What? Rand int takes one positional argument. Low, 0, length, self.buffer, evaluate. All right, well, this should work. So we're gonna do this. We're gonna say have I used I here? I think I is available. Okay, let's set I equals this. So it's going to randomly choose an index and then look at in the list for that index. So let's try running it and see if it doesn't crash this time. These are all the logs from the previous runs. I'm going to clear away some of these that I don't want. So I guess 45, 40, 56. I guess I don't want these. These are just useless ones. All right, so what we're seeing, these are some of the diagnostics I was printing out. It's winning. That's fine. It's slower. Is it slower? I feel like it was running faster before, and that could be because, oh shoot. Okay, so yeah, I mean the batch size of 10 might be slowing things down, and so I think this loop where I'm doing 10 updates is expensive. You know, it's traditionally what deep learning folks have done that has made things faster is to group the batches together into like matrices or tensors and then run it on a GPU. Here we're doing a Python loop, which is a big no-no in terms of speed. Python is very slow in loops for loops because it's an interpreted language, so it doesn't have any way to optimize. But that said, let's I mean, we can look at how it's doing. I suspect it's not going to be. I don't know actually what to expect. So we're comparing these two. We can't see anything. What? Oh, am I on wall? I'm on wall. Okay, so yeah, so we can ignore the first few iterations. That doesn't really tell us much. I guess it won a couple games. So now, yeah, I mean, this is just really slow. It's slow in a new way, right? So rather than being slow to learn, the individual steps of learning are really slow. And it might be that it's actually doing better in terms of like number of games it has to play. It might be it might learn per game that it plays. But sorry, it might learn more per game it plays, but it's taking longer to learn each step. So yeah, that loop must be really slow, and I wonder how much I can break it up so that I avoid doing like chessboard reasoning and I just store vectors. I can store the features for each vector, but I also need to remember the moves. Oh, but the moves for the next. Yeah, there's one way I can do this, which might be also slow, is to store, instead of storing the moves available in a board position, we calculate all the resulting next boards and calculate their numerical features and store those. But that feels messy. I mean, But I mean, this is really slow. It's taken, well, it's played 30 games. That's not that slow, I guess. But like, what is it doing right now? Why is it so, like, it hasn't gone to, wait. So we played a game here. And if we were to compare these runs, we can't tell a difference yet. I mean, we don't know. Like if we, if we zoom in here, there's just not enough information yet. We can't even establish an average that we can rely on. It sort of looks like the smooth value. It's like a low score, but it's only played 30 games, and like this is 1,000 games, right? At this point, the other bot had played 1,000 games, and it was still a pretty jaggy looking estimate of its score. Only at like 2,000 did it start to become somewhat readable. But we're never gonna get to 2,000 games at this rate. Well, probably what I'll do is I'll just leave it running. I can lower the batch size. Do I really need a batch size this small? I mean, this big? I don't, because, yeah, I don't. I'm gonna take the batch size down, because I mean, there's so many moves per game, and really, you only learn after you finish a game. So I'm gonna just leave it as 1. Batch size. And if I leave this running, okay, I can just do the last bit. I'll just do it, and we can leave it running, and then I can report what happens by the next stream. I will activate let's do the update for black's weights. So this is the idea. So up here, occasionally, how do you spell occasionally? Is that correct? Okay. Update black to match white's weights. I got really confused the other day writing the word weight and white, because there's a spelling of like white, like the kind of ghost thing that's very similar to weight. Right, this is whites. Okay, anyway. My current logic was not great. It was like every 100 iterations, every 100 games, it would check whether it's winning more than it loses. I don't like that much. I guess what I want is, let's say every 500 games, I could just do it every 500 games no matter what. Previously it had taken, actually let me just estimate how long it took. So for 1,000, 20,000, let me look at, well, let's look at a different run. Let's do this one. So I had 55,000 games in this one, and so these are hours. So this is 1 hour, 2 hours. So is it relative the unit hours? Yeah, I think it's hours. So I ran for 12 hours and I got 55. So, oops, 55,000. 55,000 in 12 hours. So let's say 60,000 in 12 hours. So we could do like, if we did like 5,000 games, how long would that take? Okay, I gotta do this for real. So 55,000 in 12 hours. So it's like 4,000 games an hour. So every hour I could have an update to match white's scores. I mean white's weights. That seems okay. Something like that seems fine. So let's just forget about this stuff. Whether it's winning or not, every 5,000 games it's going to update. So what we'll see is the reward value will go back down every single time, right? Every single time it updates to match the scores, you know, we're going to stop getting good rewards, right? Even if we learn to get consistently high rewards, once our opponent is as good as us, we're going to get 0 reward on average. And that's fine. So let's just try this, I guess. I don't know. Is there anything else I want to change? It still feels slower than it was. I wonder what the slowdown is. What did I change that made it slower? Because this is like, this sampling is just doing it once because there's only the batch size is, well, I mean, unless there's a bug, this batch size should be 1. All this stuff should happen the same amount of time as it did before. Oh, actually, one thing that could make it slower is I'm running OBS and streaming. That's on a Mac. It's quite CPU intensive. Yeah. So maybe that's all it is. I mean, but I'd love to see it like really fly through games, but it's just not doing that right now. But let's see. Let's look at the results for now. I mean, so far. All right. So the comparison we want to make is Fourier Features. That's the really best one. I would say that's the best one we've had so far. And you can't see anything in the reward. I mean, okay, it got a little. Well, okay, it got good and then it got bad, but it's so few games. I wouldn't count it as anything yet. So maybe we'll hit 100 games soon. 45. So if we zoom in, see, this interface does not allow me to do what I want to do. I want to zoom in like really tight here, and then I want to just drag it. But Alt lets me drag, or Option lets me drag. Okay, see, this is like still just a tiny sliver, so we haven't zoomed in enough. So we want to zoom in further. Did that not zoom? What? Why did the other plot not start until 150? What? That's strange. And it seems to really jump. It's like it only updated. Did I have a fixed interval on? Oh, you know what? It must be TensorFlow or TensorBoard. TensorBoard is trying to save computation because there's like so many data points on this plot. It simplified it. Because like I wrote to the log every single value for every step. But this goes from step 244 to step 465. So TensorBoard is just trying to simplify this curve. All right, so then if we zoom out a little bit, I don't even know how to. No, that doesn't work. Okay. Well, I don't know. I mean, is this better? We don't know. Let's compare it to like for linear only. Maybe we can see a curve difference. Linear only started out really lucky. Alt and scroll to zoom. Okay. What the heck? Okay, this is also weird. Yeah, I think once the numbers are too big, or the amount is too big, TensorBoard is simplifying it. Can I do, maybe on this interface it's a little different? Let's compare Fourier features, high temp. I have to do a lot of smoothing because the reward is either 0 or 1000 or, yeah, I mean, again, Fourier features ran for, 20 hours or something, 40 hours, and this one has only run for like a few couple minutes, and so that's why you can't even compare them. So I don't know. It's possible this is going to run faster, learn faster, and I guess there's no great way to know until we wait until get some results. I just want to keep hitting reload, but that's not going to help. Other things we can look at. These are the tables for how much each square is preferred for each piece, but it's not a great thing to look at because I had this to plot it as an image. I divide the intensity or the score by the maximum score, and then I also forgot to take into account that some of these values might be negative, and we're not seeing any of the negative squares. So it's not a great way to view these. I could have fixed it, but I chose not to because I wanted to do other things. The pawn table looks all weird. That's pretty weird that it wants to push all these pawns. I think it's just early on in its learning process. I also noticed as I ran this that it really liked to increase the value of all the pieces. For some reason, they like them bigger than they should be. And my thinking is that I think that's because I set mate to be worth 1,000. So if you checkmate the opponent, you get 1,000 reward. So because of that, you maybe the learning algorithm is saying like, well, a queen's worth more than 9 because if you capture a queen, you also increase your chances of getting checkmate. So it might be that's why it's increasing the values of all the pieces. But you would think that would make it bad at predicting the material gains that it gets as the intermediate rewards. Right? So this bot, we're giving it rewards for making captures. But it's like, oh, I mean, maybe 1,000 is too big and maybe that's the problem. But whatever it is, we want it to be bigger than all the available material. So, right, and the total material on the board is what, 8 plus 10 for the rook, so 18, and then 12 for the minor pieces, 30, 39. Is it 39? And then, I mean, theoretically, all the pawns could be queens, so it's actually 8 times 9. I mean, that's kind of silly. Maybe we shouldn't consider that, but all the pawns could be queens. Oh, and then that's for one side. Well, anyway, I don't know. I mean, it seems logical to like set checkmate to be worth like infinity. But I don't know. All right, let's see what the update is now. All right, so now it got worse. And these fluctuations might happen all the time at this level because I ran these for hours, and so that's when we saw gains. But it also could be something wrong with my code. So how do we tell? Let's see. Does this look? I mean, the win-loss rate is. If we scroll up. Okay, it's hard to tell. It kind of went up to 1, but that was early on, and then it went down a little bit. Win rate is 22. Yeah, it kind of went up and then went back down, just like the reward value, which is, I guess, not surprising. But then why is that happening? Another problem that I have with my current code is that it is storing. Sorry, it's storing the just not the code, but the logging that I have for the tensor board. It's only storing the. Where did my browser go? Oh, here. It's only storing the reward at the end of the game, so it's not keeping track of the reward that the bot's receiving for material gains during the game. And so if the reward for the winning or losing is like flat or even going down, it's possible it's making improvements on material protection, but we wouldn't see that from these plots. But I kind of doubt that. I feel like if it's gaining in material, it should be improving its win rate. These are the different weights for rook. Yeah, so let's see. Looking at, yeah, it's just increasing it. So rook is now worth 10. Queen is worth 15. Pawn's worth 4. Knight's worth 4.5. Mate is slightly less than a thousand now. And bishop is worth 5.5. Yeah, I don't know. Let's see. What else can we do? I mean, I guess I might have accomplished what I wanted, and then now we just let it run, see if it improves. But I mean, at this point, maybe we can compare. Maybe, so yeah, we don't. This is not conclusive. Like looking at this resolution of the Fourier features, we don't know. Shoot, I did not want to do that. We don't know if this means. Oh, no. This interface. We don't know if this means that they're kind of equivalent at this stage. Like the Fourier features method really began to make improvements. I guess let's zoom like this. It began to make improvements a few thousand in. So I had to see a few thousand games. I mean, like maybe we could argue that around here it's like a serious improvement. So what is that? That's like 1,000 games. So after 1,000 games, it was really improving. So, I mean, is it that we're not learning? Yeah, maybe we're worse. I don't know. There's also randomness involved here. What else did I change? Did I change anything that could have caused it to be broken? This is 0.91 now. Let's calculate off of the back of the envelope estimate of whether the buffer is full. So how many games have there been? It's been like 200, like 250 or something like that. So 250 times, let's say there are 50 move games. So the buffer's not full yet. So we haven't even seen that happen. That the win-loss rate went down again, but it's fluctuating so much at this number of games. So it's hard to say whether that's a valid measurement. Yeah, once this runs for a few hours, like both of these numbers just like slowly move, but now they're just like jumping around. Oh, another thing we can do is we can actually look at the game. But I mean, we can look at the bot, like it's running. I think in the back. Oh shoot, what is running in my background? Is my computer running 2 of these jobs? So I'm not running the learning. I'm running TensorBoard. Oh, I'm running the game. Yeah, so random players are playing us right now. When was this? Is this happening right now? 13. No, that was earlier this afternoon. I realized today that I've played my bot a lot, and like I play, I like hyper blitz speed just to like test what's happening, and like I realized that I'm probably messing up my like analytics. Like Lichess has these awesome analytics tools. Like I don't know, I probably mess it all up. Maybe I can sort by rated games because I don't play my bot rated. But anyway, I'm just gonna log in as the bot and challenge like Stockfish so we can watch it. So what we should see at this stage is that our bot still is terrible because it's doing the thing that it's going to do this sure, let's play bullet speed. I mean, it'll actually beat Stockfish level 2, I think. Oh, casual games don't count for insights. That's great. That I'm glad to hear that. Oh, okay, this is too fast for us to think about, but we're gonna watch our bot's gonna hang pieces all over the place, but so will Stockfish at level 2. Like, okay, maybe this is not too informative, and it shouldn't be. So we don't expect this to be that different from the other bot. The only time that this will be different is if, assuming it learns. Okay, there's two things that we did today. We made it hopefully learn faster against any opponent. And then that's the first thing. And it might not. The second thing we did was we are going to slowly improve the quality of the opponent. And we haven't gotten to that. That's going to happen basically roughly every hour. So I'm not going to stay on stream long enough for that to happen, but it'll happen, as I leave this on overnight. And then what we hope to see is that as it plays a more difficult opponent, it will learn to actually protect its pieces, and actually try to, I don't know, only make captures that are safe. Right. Whereas right now it's just learning. I mean, I'll give you an example of what. Let's see if we can find an example of it doing something really dumb. Like, so again, it's not much stronger than its opponent right now. So like who it's training against is basically the same as itself. So if we see a mistake that our bot makes right now, it's similar to, like, what was that? I mean, this was a random move because there was no. This is a random move that doesn't change material, but it just instantly loses material on the next turn. But the bot doesn't know that, right? It has no notion of that. So that's one example. But I think another example that will come up is if my understanding is correct. As soon as a capture is available, it's going to take it. So let's watch for one of those. Like no. So well, okay. Right. So it's going to capture back, right? Is it? No, it didn't. Okay, I expected it to capture back, but maybe it's already learned. I don't know. That's weird. I would think that the initialized bot would capture back. Like if you think about the scores, it would just, it's like, oh, I get to improve material imbalance by 1. In fact, in this case, I think it should capture back. Right? Every checkmate is protected. I mean, it loses a center pawn, but yeah, yeah, I don't know why. I don't know. So that's weird. Yeah, here it took the pawn instead of the knight. I don't particularly see a reason that would be correct. So yeah, so I don't think it's just, that's not good. Oh, it could be, I mean, and not, correct or not, that could be just because the scoring right now, maybe he likes pawns. Let's see what it likes. Oh, look at that. So the reward is still low, so could be something wrong. Oh, you know what? I could probably, all that stuff I was worried about the different reward, like naming of variables, I could have definitely introduced a bug there. And if I'm like scoring the wrong reward for different positions, it could be learning like nothing. Oh, was there a mate in one? Oh, wait, where's mate in one? Oh, that, yeah. Stockfish, yeah, well, Stockfish level 2, that's what you get. Right, so what was I saying? I was, oh yeah, I want to check that bug. I mean, I'm worried that, that I have, like, so pawns are worth, wait, let me turn off the red one. So pawns are worth 4, knight's worth 5.5, so it still should have taken the knight. So I don't know why. There could have been other rules in the neural network, but let me check this. This is like what I'm worried about. So I'm pulling out of our replay buffer, right? I pull the position and the next move out of the replay buffer. So I want to really make sure I'm not using any of this stuff, right? This is the new position that we received. This is the stuff we want to learn from. Yeah, it's not only not taking, right. So like, those are the two things, right? We care about mate, which is worth 1,000 or minus 1,000 if you lose it, if you're checkmated yourself, and then it didn't gain material when it should have, so it just wasn't behaving, the way we wanted to. Okay, so battery word. This also could be the temperature thing. So I'm scoring all the positions, then I'm exponentiating it, and I'm randomly sampling from a distribution defined by that exponentiated score. And that can mean that it could play a suboptimal move, and which we wanted to do. We wanted to play up suboptimal moves, so that it can learn, because it doesn't actually know what's optimal, right? So what it thinks is optimal might not be correct. But there might be, the proper way to do this in reinforcement, sorry, not proper, the more traditional way to do this in reinforcement learning is you do what's called epsilon greedy, where you have some probability epsilon, some small probability that you'll play a random move, and otherwise you play the best move according to your current score. And I didn't want to implement that for okay, there's no good reason I didn't implement that. I just wanted to try this other thing. Yeah, sure. Okay, so let me just read through this to make sure there's no obvious bug, and then otherwise I'll just end the stream and let it run. I mean, this might be, yeah, it might be making slow progress. Yeah, it could be making slow progress. There's always some randomness in this. But let me check this. All right, so we get the ith entry. We pull out the ith entry, and we get batch stuff: batch reward, batch prev board, batch prev move, batch new board. Then we want to get all the moves that we can consider from the next position. So batch new board, legal moves. If there are no legal moves, we set it to 0. If there is a legal move, then we find the max action score for the new board given the move for all the possible moves. That's correct. Then the batch previous board, on that we add the next move. Sorry, not that we add the previous move, the move that we actually took. Yeah. Then we get the features for that. And then we return it to how it was, and then let's check this learning weight update. So it's the reward that was from the batch, the max feature score, which we calculated using the batch position, the action score from the, yeah, I mean, this looks correct. Descriptors for what we calculated before. Yeah, it looks like what I intended. I mean, yeah, I say correct, but it's what I intended. So, I might have intended something that's incorrect, but it is doing what I intended. So it's possible that it's running just slowly. It it might or might not actually be faster. Yeah, not clear if it'll be faster. Yeah, the reason it's supposed to be faster is just like if you just learn from the moves that you most recently saw, it could be biased toward like let's say you train your bot, let's say their weights go in the wrong direction a few iterations, then you're starting to play really poorly. You'll really focus on those poorly played positions, and that's kind of like the bias you want to avoid. And this sort of randomizes it over your entire history. Um, but that's the intuition anyway. I wonder if, and it's possible that this intuition works only for, well, I mean, everything that they did for this Atari paper was like translated into alpha Go, and then was eventually translated toward Alpha Zero. But they probably, they definitely made modifications along the way. So I didn't read the Alpha Zero paper to see if they use this as well, which I could do. I don't want to do it too much, right? Because at some point then you're just like, I'm just re-implementing Alpha Zero, and that's not too exciting. I don't want to like look at all the different concepts that people have been throwing around through this for reinforcement learning over the years and just try to mix them up in the way that I think makes sense for chess. But yeah, at some point I could just check the, how they implemented it and then mimic it similarly, or approximately mimic it. So yeah, the win-loss ratio is almost 1. It's that's a little generous, but it's getting close to even, which is weird. Why did it get worse than, like, when I initialized them, they were like equivalent bots. So I don't know why it's not able to start out well. Well, it's pretty even now. It's almost at 0. But again, that doesn't mean it's good. Let's just try another game. I bet it can beat 1. No, how would it beat 1? And it can't even beat a bot that looks ahead 0 moves. So, all right, let's try level 2 again, and it should be fine. Yeah, so I left that pawn hanging for a while. Oh wait, what? Stockfish just. I think Stockfish. This is okay. Okay. Well, I don't know how good of how insightful this is, because both engines are playing pretty randomly. But no, yeah, okay. Now Stockfish is playing like an actual engine, and we're not an actual engine yet. That makes more sense. Yeah, initially that was a little weird when it dropped its queen and then didn't capture back, or didn't drop the queen. It didn't capture back after we captured its queen. Wait, when did Stockfish get that rook? Okay, so here it prefers rook. Wait, what's happening? The clock was running out? Did the program crash? I should have played. Oh, maybe because I was flipping around, it messed up the program was confused. I don't know. That's weird. I don't know why I didn't make a move. But yeah, okay. So we're not seeing anything better, which we shouldn't expect. I mean, at this stage, we can see from the scores on TensorBoard, it's barely equal against its default, terrible opponent. Now it's a little slightly better. Yeah, I guess I think just comparing against this other run, it looks worse, but it's hard to tell because the resolution on that other run is quite low, and this could have just been like some weird fluctuations. But this looks pretty consistent. But again, this resolution also is quite low, so I don't know what to read of it. It's really like I'm not sure that we'll have a definitive comparison until we get to something like this, which just takes a few hours. Oh shoot. Once I clicked here, I can't let go. As soon as I let go, it's going to zoom into some place I don't want. And there's no undo. Yeah, TensorBoard is like really elegant in some ways, but in other ways it's pretty clunky. Yeah, I wonder if this is actually better. I mean, we don't have, if I compare against any of the other ones, I think any of the numbers we had at this number of games is not reliable. So there's hope that it's actually gonna do better. Or maybe the other possibility is it might do better like in this regime, like out here where where the traditional QLearning gets kind of stuck, it gets flat. It might be that we can do better there because we can continue learning from old games. I don't know. The experience replay stuff is it's based on intuition, and I think there's been some papers that try to justify it with theory, but I feel like with computer science theory, not chess theory. But it seems a little questionable to me, like whether it's actually better to use older game positions or to use fresh ones. Like the idea is that by using positions that you reached in the past, that's like an older version of yourself that you're training from, or you're training based on moves that you made using an older version of yourself. Which the question is like, do you really need to train from those positions? I don't know. I think the argument is that sometimes you do, and that's why it helps. But yeah, and then there's also the intuition to like human learning, right? If we think about how we learn as humans, if we play a game and we, learn about a particular tactic, is it useful to like go back and like restudy previous games? I mean, yeah, I guess it is. It's good to just not yeah. This is what QLearning does without experience replay. It's as if you can only learn from the last game you played, and you can never remember anything whatever you learned, whatever you studied after from like a week ago, you're never allowed to look that game up again. That's what experience replay fixes. It allows the bot to go back and look at it, its previous games and say, there's stuff I haven't fully mastered from this game. I can still learn from it. So I guess that's the intuition. But yeah, that's what it's doing now, and we'll just see. I don't know. There's not much to say because it's so slow. It's going to take a while. It's going to take a while for us to see any results. So I guess this is just it's just me blabbering on. So I'll wrap up the stream and I'll report back soon with I don't know how soon, but sometime in the near future with how this ends up going. Let's just have one more look before I close. I'll just turn off all these. Can I just do this? This is our current run. Yeah, we're just barely above 0, so we'll see. All right, we'll see if it works. I mean, and the other big test is at 5,000 games, it's gonna then copy the white weights to the black player, and we'll see. Hi, Lord Cobra. Yeah, you can check out the archives. I'm posting everything on YouTube. I'm gonna wrap up today, but just check out stuff on YouTube or stay tuned. I'll join. I'm not joining. I'll have another stream sometime in the next few days. All right. Have a good week, everyone. Bye.